In the previous lectures, we have looked in turn at translational symmetry, which as we learned is a defining characteristic of all crystals, and then also point group symmetry, which as we'll see is also present in crystals. In this lecture and the ones that follow, we're going to see how those two different types of symmetries can be combined. So if we were to combine translational symmetry and point group symmetry, the new symmetry that emerges that has both elements is called, in 3 dimensions, space group symmetry, and in 2 dimensions, plane group symmetry. This lecture we're going to focus on the simpler 2-dimensional case, but then in the lectures that follow we will talk about 3-dimensional space group symmetry. So remember that in 2 dimensions we have already learned that there are 5 and only 5 Bravais lattices, and those lattices are shown here. We've got the oblique lattice with the parallelogram unit cell, the square lattice, the rectangular lattice, which comes in 2 flavors, a primitive rectangular lattice with only lattice points at the corners of the unit cell, and the centered rectangular lattice, which has an additional lattice point at the center of the unit cell. And then the 5th type of lattice is the hexagonal lattice. We haven't talked about point group symmetry in 2 dimensions, but the 2-dimensional case is considerably simpler than the 3-dimensional case. Because we don't have a 3rd dimension, there are several symmetry elements that we don't have to think about in 2 dimensions. For example, there's no inversion center, because the inversion center would be exactly the same as a 2-fold rotation axis. Because there's no inversion center, then there's no roto-inversion axes, so we don't have any improper rotation axes. There is no screw axes. And of course, we don't have to consider perpendicular symmetry elements, perpendicular mirrors, or perpendicular rotation axes. And because we're talking about crystallographic point groups, we only have to consider rotation axes that are 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold. So because of that, there's actually only 10 point groups in 2 dimensions, and those are shown here. We have the point groups that arise from just a rotation axis, and then the point groups that arise when we have a vertical mirror plane. Okay, so now how can we combine those 5 Bravais lattices and these 10 point groups to get these new symmetry groups, which we call plane groups? Let's start by just thinking about the translational symmetry first. So here is a collection of lattice points. This is an oblique lattice, so there's no special symmetry here. And if I wanted to build up some kind of crystal or some kind of pattern, I have to associate an atom or an object with each lattice point. I have to have a motif. So let's make the motif this Chinese character. And now, if we just apply translational symmetry, we would have to have that character be this particular distance and orientation from each lattice point. So this lattice has translational symmetry, obviously, but there's no real point group symmetry here, other than just, let's say, the identity. Well, let's go to something a little bit more complex. Let's keep the same lattice, keep the same character, but now let's put a point symmetry element into the crystal. Let's say that we have a 2-fold rotation axis at the center of our unit cell. So because of that 2-fold rotation axis, we're going to generate another character here, and you can see that its orientation is dictated by the rotation axis. Now, if we apply translational symmetry, all of the unit cells have to be the same, and so now we get this pattern of characters or symbols. Okay, now if we look carefully, there's a couple of things we want to note. First of all is now this 2-fold rotation axis has to operate not only on just these 2 characters that are inside the unit cell, but it has to be applicable to all of the characters in the infinite array of characters. And so you can see that's true. If I were to, let's say, operate the 2-fold rotation axis on this character, it's going to end up down here. If I were to operate it on this character, it's going to end up down here. So the application of translational symmetry here has not destroyed that twofold rotation axis. The other thing we see is that there are additional twofold rotation axes that are created by the translational symmetry. Maybe the easiest one to see might be here at the lattice point. So that would take this character and move it over here. There's also one at the center of this edge of the unit cell that takes this character and moves it here. There's one at the center of this edge of the unit cell that takes the character and moves it here. I'm not going to draw them all in, but what we would see is that at every lattice point, there's a twofold rotation axis. And at the center of each edge, and then at the center of the parallelogram, that's a unit cell. So in this depiction, we can see the synergy between the translational symmetry and the point symmetry. Now, let's stick with an oblique lattice, and I'm going to draw the unit cell around the lattice point here for convenience. But let's now put in a threefold rotation axis at the center of the unit cell. Okay, so that would generate these three characters. Okay, and now let's apply translational symmetry. Okay, and so every unit cell must have those three characters in that orientation. When I look at this entire pattern of characters here, is the threefold rotation axis retained? And the answer is no, not really. If I were to rotate, let's say this character up here by 120, where's that going to go? It's going to go kind of down here. It's going to be pointing in a different way than this one. It's a little hard for me to say exactly where things are going to go, but the point being that when I apply the translational symmetry, it destroys that threefold rotation axis, because the rotation axis has to operate not only on the things within the unit cell, but on the entire crystal. And so from that, what we learn is some symmetry operations are inconsistent with some kinds of Bravais lattices. So in an oblique crystal system, we can't have a threefold rotation axis. And so that would take us to this classification. It turns out that in each of the Bravais lattices, there is a required symmetry element. So for the oblique lattice, as we just looked at, there are no symmetry elements that are required. We don't have to have any kind of rotation axes beyond the identity. But we could have a twofold rotation axis. When we come to a rectangular lattice, either primitive or centered, we'll see that there has to be a mirror plane. There could also be a glide plane. When we talk about the travel symmetry elements in the two-dimensional case, screw axes are not present, but glide planes are allowed. So the mirror or the glide is the defining symmetry element of a rectangular lattice. When you talk about a square lattice, the defining symmetry element is a fourfold rotation axis. And when you talk about a hexagonal lattice, it's either a threefold or a sixfold rotation axis, or both. And so because of that, what we see is that each of the 10 point groups is associated uniquely with one of the Bravais lattices. So if the point group is 4 mm, well, the Bravais lattice has to be square. It can't be one of these others. Because of that, once we know the point group, we know the Bravais lattice, because they are uniquely associated with one another. So let's take a look at the different plane groups that can arise. If we were to look at the oblique case, right, we just saw that there are two possible point groups that could have an oblique lattice. Point group 1, which has just the identity, and a point group 2. And so the symbols for the plane groups that arise when we combine translational and point symmetry are P1 and P2. And here you can see these twofold rotation axes, right? We saw that just a minute ago when we were looking at that oblique pattern. We saw that the twofolds were on the lattice points, at the center of the unit cell, and at the center of each edge. When we go to the primitive rectangular Bravais lattice, we have either PM or P2mm. Right? And so here we see those two. We see the spacing between the mirror planes in both of them. And we can see that in 2mm, of course, there's also a twofold rotation axis. But as it turns out, these are not the only primitive rectangular plane groups. And the reason why is because we could swap out the mirror plane and add a glide plane. And if we were to do that, PM would become PG. Right? The P stands for primitive. Here we see that because in a crystal we can have these travel symmetry operations, we can have the glide plane, that we have different plane groups for a mirror versus a glide. We could also, instead of having P2mm, if we replace the mirrors with glides, we get P2GG, the G is standing for glides. It's also possible that we have mirrors going in the X direction and then glide planes running perpendicular in the Y direction, and that's point group P2MG. Now, what about the centered rectangular? So you might think, well, okay, I'm just going to do the same thing for the centered rectangular, and we should have 5 plane groups for centered rectangular. But it turns out there's actually only 2, just CM and C2MM. But you might be wondering, well, what about CG or C2GG? Why don't we have those? And part of the clue is that if you look at CM, you can see that, yes, it has these mirror planes. Remember, those are the solid lines. But there's also glide planes. So the mirror and the glide come together. So CM and CG are not uniquely different plane groups. They're the same plane group. And the name for that plane group is CM. A similar kind of logic can be applied to C2MM, because here we also see both mirrors and glide planes running in both the X and the Y directions. Now you might be wondering though, well, why do the mirror and the glide go together? And to understand why that is, let's take a look at this hypothetical plane group where we have centered rectangular, lattice points at the corners and at the center, and then we have just a glide planes running in the X direction. I've placed the glides between the lattice points because you see that's the placement we would have that would take this lattice point and move it to this lattice point. Okay. Now let's put in our character. Let's say that we have one object in the unit cell. And let's see what other objects are generated by symmetry. So because of the translational symmetry, we have to have that same character, the same distance from each lattice point, and the orientations being all the same. So that gives us these additional characters. Now let's operate with the glide plane. We are going to start with the upper glide plane. If we operate that one, we're going to have a mirror, translate by half the unit cell, and then we get this character. And if we were to now do an operation with the lower glide plane, we get this character, right? We're going to mirror and then translate by half a unit cell. Now, let's take some of these points like this one and translate by an entire unit cell, right? By translational symmetry, we have to have the same set of characters around each lattice point. And so you see now there are 2 characters associated with each lattice point, and that's because of the glide planes. But if you look at this pattern for a minute, you'll see that we have created some mirror planes now. Right? There's a mirror plane that runs horizontally through the middle of the unit cell that relates these 2 characters and all of the others. And there's mirror planes that run through the edge of the unit cell, the horizontal edges. You can see now that if I have a horizontal glide, I'm going to get horizontal mirrors. And so CM is exactly the same thing as CG, and the name we use for that plane group is CM. C2MM is the same thing as C2GG, because the mirrors and glides go together, and the name for that plane group is C2MM. We can look at the square plane groups, and so you can see there's P4, no mirrors there. P4mm, where the mirrors intersect at the fourfold axis. And then P4GM, where you can see the glide planes are now intersecting the fourfold axes, and the mirrors intersect the twofold axes. So these two, P4mm, P4GM, are different. And then we can go to the hexagonal plane groups, and it turns out there are 3 of these that are based on point groups that have a threefold rotation axis, P3, P3M1, P31M. These latter 2 differ, once again, in the relationship of where the mirrors are with respect to the rotation axes. In P3M, the mirrors intersect the threefold rotation axes, but that is not the case in P31M. And then finally, we have 2 plane groups that come from point groups that have a sixfold rotation axis, P6 and P6MM. And we see that P6MM also has not only a sixfold rotation axis, but a threefold rotation axis, as well as a twofold rotation axis. It's a little bit confusing, but the lighter lines, like this one here or this one here, those don't represent mirror planes. Those are just telling you something about the unit cell, and by some convention, the hexagonal unit cell has lines that divide it up into 2 triangles. Actually, I'm not sure why that is. I think it's just for ease of visualization. Then the somewhat wider or bolder lines, those represent mirrors. So you have to be a little bit careful not to confuse the boundaries of the unit cell, the light lines, with the mirror planes. One last thing we want to say about the plane groups and reading these diagrams and using what we're going to get into a lot more in the next lecture, which is the international tables for crystallography, is to talk about sites within the unit cell. This diagram here is going to show you all of the symmetry elements in the unit cell. This is plane group P2MM, and we see where we have the twofold rotation axes, and then we see that we have these mirror planes. The other diagram that you'll find in the international tables, shown here on the right, gives you what are called the equivalent positions. Each circle might represent something like an atom. So let's say that we put an atom, but it could be an object, here in the unit cell. What this diagram is telling you is that all of the other circles here are going to be generated by the symmetry operations of this plane group. The ones that have a comma in them, that means that the handedness is switched. So if you have an object with chirality, say for example like a hand, and you reflect through a mirror, you're going to get the opposite-handed representation of that object. Whereas if you rotate by a twofold rotation axis, you would not change the handedness. Okay, so that's what this diagram shows us. Even more useful is this table below, which gives what are called the Wyckoff sites of the plane group. So let's start at the very top. The top one is always what's called the general position. And so this would be for an object that is not on any particular symmetry element, for example, like this circle. And what this tells us is if you put one object in the unit cell, you're going to get 3 symmetry equivalent objects. So if we had an object here, let's just say an atom, that were at coordinates x, y, we are also going to get, because of this mirror plane, we're going to get this symmetry equivalent atom, which is at minus xy. We are going to get this symmetry equivalent atom, which is at x minus y. And then we're going to get this symmetry equivalent atom, which is at minus x minus y. And then when we apply translational symmetry, we can see that we get these 4 points at each lattice point. All right? So that's what's called the general position. It has a multiplicity of 4. That is, there are 4 atoms on this site at these coordinates. And the symmetry on which this object resides is 1. It's not sitting on any given symmetry element. However, there are positions within the unit cell, which are called special positions, where you might put an atom on a symmetry object. These ones that are 2e, 2f, 2g, and 2h, those all have coordinates that would refer to putting an atom on a mirror plane. So let's say we put an atom right here on a coordinate that might be x, 0. You can see that that is on what is called Wyckoff Site 2e. The site symmetry here is a mirror plane. We're sitting on a mirror plane. And the equivalent coordinates are x0 and minus x0. And the reason why we have only 2 instead of 4 is because the mirror plane doesn't move the atom at all, doesn't generate any new symmetry equivalent atoms. But the twofold rotation axis still works, and so that takes it from x0 to minus x0. So there are 4 Wyckoff sites that represent being on different mirror planes in the unit cell. And then we also have 4 Wyckoff sites that have a multiplicity of 1, and those represent putting an atom on the twofold rotation axis, which is also the intersection of 2 mirror planes. So the site symmetry there is 2 mm, and if you put an atom, for example, at half-half, well, you're not going to get any other symmetry equivalent atoms in the unit cell, because the mirrors and the twofold rotation axes are just going to map this atom right back onto itself. And we'll come back to this when we go to 3 dimensions. Well, let's finish this lecture by seeing if we can identify the plane group of some kind of 2-dimensional tiling pattern. So take a look at this pattern and see if you can work out what is the 2-dimensional plane group here, and then what is the unit cell. And then you might want to check and make sure that your symmetry elements are at the right place in the unit cell, like they were in the diagrams that we went through earlier in the lecture. If you don't know exactly where to start, my advice is, first of all, look for symmetry elements. Look for rotation axes or mirror planes, because we learned that if we find certain symmetry operations, for example, if we find a 4-fold rotation axis, it's got to be a square lattice. If we find a mirror plane, it can't be an oblique lattice. So that kind of thinking is useful. I'm going to shut up for a minute here. I'm going to let you solve this problem, pause the video, and then when you've got a solution, come back and we'll go over it together. Okay, welcome back. Well, it's a little bit tempting to look at this and say, I have these squares here, so I must have a 4-fold rotation axis. And if I had a 4-fold rotation axis, my unit cell should be a square, and my plane group should be one of the square plane groups. But a little bit closer inspection reveals that there's actually not a 4-fold rotation axis in this pattern. If I were to, let's say, come right here on the center of this square and rotate by 90 degrees, I mean, the square would be the same, but this, let's say, hourglass-shaped thing would come down here, and it would be pointing horizontally, not vertically. Okay, so there's not a 4-fold rotation axis here. What symmetry elements are present? Clearly there are symmetry operations here. And so I can see some 2-fold rotation axes. The 2-fold rotation axes come at the center of each square and also at the center of the hourglass. And I think it's pretty easy to see that there are some mirror planes. There are horizontal mirror planes as shown here. There are vertical mirror planes running as shown here. This is not a centered lattice in any way. I don't actually see any glide planes in this crystal structure. So this is going to be a primitive rectangular plane group, and that plane group is going to be P2MM. You can go back and look at the diagram if you want to convince yourself of that. And in P2MM, we have 2-fold rotation axes at the corners of the unit cell, at the midpoints of each edge, and in the center of the unit cell. So this would be our unit cell. Now, it is true that the dimensions of this unit cell are very close to a square, but that doesn't make this a square lattice. What defines the lattice are the symmetry elements, and because there's no 4-fold rotation axis here, this is not a square lattice, this is a primitive rectangular lattice. All right, well, that's enough about 2 dimensions. In the next lecture, we're going to extend these ideas into 3-dimensional crystals.